Welcome everyone to this week's Science News. Today we'll talk about Wavelike dark matter, wires that learn, the core of planet Mars, why Quasars Ignite, a superconducting highway, fabric that changes shape and color, chemistry on a quantum computer, the Brazil nut effect, and of course, the telephone whirring. A lot of you have asked me to comment on a paper that made headlines last week with the claim of having found evidence that dark matter is wave-like and it's got something to do with space-time crinkles. Dark matter is supposedly stuff that fills most of the universe, and if it exists, which it may not, then it's even more abundant than normal matter. Averaged over the entire universe, it'd have to make up about 85% or so of all matter. But in galaxies, it's usually even more, 90% and up. Yes, that's also the case in the Milky Way. Its mass is mostly dark matter, which forms a big spherical halo like a huge invisible cloud around the visible disk. And if it exists, dark matter is passing through us as we speak. The currently most popular hypothesis is that dark matter is some kind of particle. Astrophysical observations, unfortunately, tell us very little about exactly what kind of particle. They just tell us where the stuff is and how much of it there is. This is why physicists have put forward hundreds, if not thousands, of different hypotheses, a completely fruitless strategy that I've bitched about in an earlier video. Now, all particles are also waves, because quantum mechanics and all, so the headlines make little sense to me, even leaving aside the question of what a space-time crinkle is supposed to be. Is this like a French fries crinkle cut? Do you want ketchup with it? What they say in the paper is that they test ultralight particles as constituents of dark matter. One type of those particles are invisible axions. This is an option which has become increasingly popular among physicists in the last decade or so, partly for good reasons and partly for not so good reasons. The thing is now that the lighter the particle, the larger the wavelength that's associated with the particle. The dark matter particles could be so light indeed that the wavelength becomes comparable to the size of a galaxy. And stuff that has wave-like properties can interfere, and that can create specific patterns. The authors of the paper looked at a particular gravitational lens. In a gravitational lens, one galaxy curves space-time, and the light from a second galaxy then bends around the first. For this particular galaxy, the result of the gravitational lensing is somewhat confusing, with multiple dots, and it has been difficult to explain. This is because in the usual dark matter models, the dark matter halo is very smooth, and therefore the lensed image should also be smooth. Though personally I don't find this particularly surprising, because there's a lot of stuff going on out there that we don't know about, so you get a lot of weird observations. In any case, what they now do in the paper is to add random perturbations on the smooth dark matter halo, choose the parameters suitably, and show that this fits the observations better. So, no waves, just random fluctuations. That's what they mean by crinkles, and no ketchup either. A few things worth mentioning. First, they don't actually use any wave-like properties of the dark matter. That's just an inspiration for adding random bumps on a smooth halo. Second, massive particles could also create halos with inhomogeneities, or crinkles if you wish. Depends on their self-interaction, about which we know very little. Third, it's unsurprising that if you make a model more complex, you can fit the data better. In summary, I'd say the results do not support the conclusion. Albert also thinks this is a little sketchy. An international team of researchers has developed wires that learn like the human brain. They took a bunch of tiny silver nanowires and splattered them on glass. This created a network with about 700 nodes. They sent currents through the network, which they used to ask questions and extract answers. Then they trained the nanowire network by providing feedback signals that either increase or decrease the conductance of the junctions, depending on whether the network's output was correct or incorrect. This is very much like learning works in the human brain, in which connections between neurons strengthen or weaken. The wire network could also remember things at the same time as they were processing new information, also very similar to the human brain. The artificially intelligent systems that we use at the moment, in contrast, do not learn on a physical level. The physical level remains the same. They learn on the software level. The researchers also ran the wire networks through what's known as the N-back test, a common working memory task for humans. It's a bit like the game concentration, when you turn over pairs of playing cards to find two that match. You have to remember which card is which from earlier turns. Typical humans can recall about 7 steps back. So could this nanowire network. Who knows, that box with old cables you have in the basement might soon enroll for college. An international group of researchers has found out that Mars probably has a liquid core, and it's smaller than previously thought. They arrived at that conclusion by analyzing seismic data from 2 Mars quakes in 2021. One quake was likely from a rock fracture caused by heat or stress. The other was triggered by the impact of a meteorite. Being hit by a meteorite is not great if you're Mars, but it is great if you're a seismologist studying Mars, because in that case you can very sharply pinpoint the source of the initial waves. The data came from NASA's InSight Mars lander, which retired from duty in December. On the left you see one of the last images it took, the seismometer on the surface of the planet. Scientists can use seismic waves from earthquakes to figure out what is going on inside a planet, because the waves move at different velocities depending on what they encounter. In the new paper, they tried different possibilities for the size and composition of the core to see which one fit the data best. They found that the best fit was a core radius of about 1,800 kilometers. For comparison, the core of Earth has about twice that radius. Like Earth's core, that of Mars is mostly molten iron, but on Mars it contains about twice as much light elements. Those light elements include a lot of sulfur plus oxygen, carbon and hydrogen, which together make up about 1/5 of the mass. Our Sun and its planet all formed from the same protoplanetary disk, but they don't have the same share of chemical elements. Scientists have models for how this happens, but very little data. The composition of Mars is the obvious place to start. It's also a message to all fitness gurus on TikTok. Some of us were born with a liquid core of low density. Please leave us alone. Astronomers at 2 British universities have figured out the main reason that quasars ignite. Quasars, short for quasi-stellar object, are among the brightest objects in the universe. They are black holes that sit in the center of some galaxies, and they suck in huge amounts of gas. The gas swirls around the black hole and heats up. That emits a lot of radiation, so much that we see it as a brilliant light even from billions of light years away. But not all supermassive black holes are quasars. For example, the one in the center of our own galaxy isn't. So why do some of them ignite and others not? The British astronomers looked at the properties and shapes of 48 galaxies with quasars and compared them to 100 galaxies without quasars. The observational data came from the Isaac Newton telescope on La Palma in the Canary Islands. They found that nearly 2/3 of the galaxies with quasars showed distortions in the outer regions, evidence of galactic collisions. By contrast, only 22% of galaxies without quasars showed those distortions. They concluded that the dominant trigger for the formation of quasars is the collision of galaxies. Moreover, in 61% of cases, the quasars were visible before the nuclei of the colliding galaxies had merged. That means that rather than being formed at the peak of the merger, they can be formed before that. I don't want to be morbid, but you all know that I want to. This finding is probably a prophecy for our own galaxy. In about 5 billion years, the Milky Way is projected to collide with Andromeda, and who knows, maybe we'll make a quasar too. So the future may be brighter than you thought. A team from the US and Germany has developed a vision for a superconducting highway. Yes, you heard that right. It's a riff on the old idea of magnetically levitated trains, or maglev trains, some of which are in use in Japan and China. Maglev trains work with superconducting alloys that repel magnetic fields very strongly enough to levitate a train carriage. This dramatically reduces friction and allows the train to reach much higher speeds. Maglevs are rare because superconductors must be cooled to extremely low temperatures, which costs a lot of money. This concept paper proposes to combine maglevs with hydrogen transport, because, as you've probably heard, we're supposed to get this wonderful hydrogen economy. The trouble with hydrogen is, well, many things, but for today's purposes, it's that to transport it, you need either high pressure or low temperature. So the authors of this paper want to run liquefied hydrogen at about 20 Kelvin through highways, and that way convert the highway into one large superconductor. Here's the plan. See all that liquid hydrogen coming from the factory off to the side of the road? It's cooling for the road and at the same time storage, plus helping transport the cars on the road. There's a layer of liquid nitrogen and a vacuum layer on top of the hydrogen to keep the hydrogen cool enough. And then all you have to do is fit the undersides of vehicles with permanent magnets. That'll make the vehicles levitate over the superconductor highway, and they can zoom to their destination at 500 to 800 kilometers an hour. Sounds like fun. Just don't step on the highway, you might freeze to the ground. For the experimental part of the paper, they levitated a magnet above a superconductor. The rest of the technical details are still to come. Oh yeah, plus the financing. Maybe Elon will be interested? No luck today. A group of Canadian and Chinese researchers has created a fabric that can change both color and shape when either heat or electricity is applied to it. When the fabric cools down or the voltage is removed, it goes back to its original shape and color. Earlier smart fabrics have been capable of changing color or shape, but not both. This new smart fabric is woven on a loom from two different types of plastic yarn. You can see it here in this video. One type of yarn, the blue one, is plastic mixed with a material that changes color when it's heated. The other is plastic plus fibers of stainless steel, which conduct electricity. The color changes in 20 seconds when the heat goes from 20 to 60 degrees Celsius. The researchers made a simple fabric model of a dragonfly. If you squint your eyes, you can see it here in this video, and heated it up. You can see its wings unfold as it turns from purple to blue. Once the heat is turned off, it goes back to its original shape. Well, somewhat. The recovery ratio was nearly 80% after repeated transformations. The changes can also be specific to just part of the fabric, as you see here in this video. When the voltage is applied only to the left side of the fabric, the left changes. If it's applied to the right changes. The researchers say that such fabrics could eventually be used as wearable biomedical devices or as environmental sensors. Or maybe they could use them to make compression socks that I can put on without ruining my nails. Hello. Guten Tag, Olaf. I'm not talking to you because last time I did, no one had any idea who the German Chancellor is. A 6-hour trip in a hot air balloon for $130,000? Well, I guess at least the hot air is in character. Where does it go? A round trip. That's a lot of money just to go back to where you started from. But then I guess that's what politics is all about, isn't it? I'm sure people will understand that. Tschüssi! A group of Swedish researchers has done simple chemical calculations on a quantum computer. They used an existing quantum computer at Chalmers University in Sweden and a conventional computer in addition. They fed the same simple reference problem into both computers, in this case calculating the ground state energy of some small molecules, hydrogen, helium hydride and lithium hydride. Then they used the difference between the solutions to the reference problems to correct for noise on the quantum computer. This allowed them to improve the accuracy on the quantum computer by a factor of 100, as long as they combined it with an earlier correction algorithm. So, they did a calculation on a quantum computer, of which not only the result was known, but that could have been done faster on a conventional computer. Then they corrected the errors on the quantum computation with the conventional computer. Okay, that was a little underwhelming. A group of European chemists and physicists have conducted an experiment showing the so-called Brazil nut effect without the need for external energy. The Brazil nut effect is named after the phenomenon of shaking a bag of nuts only to find that the largest, the Brazil nuts, gather at the top. This happens because it's more likely for the small pieces to fall down through the large ones than the other way around. But it only happens when you shake the bag. Theoretical models suggested that the same Brazil nut phenomenon could happen spontaneously under the right conditions. And this is what they showed in this new paper. They used a mixture of different sizes of charged particles made of a hard plastic in some kind of oil. They don't have to shake the mixture because the shaking is provided by Brownian motion, the random tiny movement of atoms as they bounce off each other. And indeed, the larger plastic particles, the green ones, move upward more easily than smaller particles, which are colored red in this video. It's because they have a greater charge, so they repel each other more strongly. It only works under certain conditions though. You need particles with sufficiently large charges compared to their mass. When masses were too large or when the charge was too low, it didn't work. How matter arranges itself is an important ingredient for models of stars and planet formation. It also helps us understand how sediments are laid down in geology, archaeology, and in children's bedrooms. Humans are funny creatures if you think about it. Pretty much everything we know, we learn from others. Our entire civilization is based on how we manage knowledge and education. We used to do that in schools, but if you want to try out a fresh and new approach to learning, check out Brilliant, who have been sponsoring this video. Brilliant offers courses on a large variety of topics in science and mathematics. All their courses have interactive visualizations and follow-up questions. Some even come with demonstration videos for experiments and executable Python scripts. And Brilliant lets you pursue your own interests at your own pace. Whether you want to know more about solar panels, neural networks, astrophysics, special relativity, or computational biology, Brilliant has you covered. And they're adding new content each month. I even have my own course on Brilliant that's an introduction to quantum mechanics. It starts from the very basics and doesn't require you to bring background knowledge. My course covers topics such as interference, superpositions and entanglement, the uncertainty principle, and Bell's theorem. And afterwards, maybe you want to continue learning more about quantum computing or special relativity. If you're interested in trying Brilliant out, use our link brilliant.org/Sabine and sign up for free. You'll get to try out everything Brilliant has to offer for 30 days, and the first 200 subscribers using this link will get 20% off the annual premium subscription. Thanks for watching. See you next week.